This is question 9 from the third CSAT sample paper. In this question, we're given a picture of a straight line joining 1 on the y-axis to A on the x-axis. And there's a bunch of squares drawn underneath, each one resting on the axes or on the previous square and touching the line at the corner, so they all lie underneath like this. And then we're told to imagine that the squares go on forever, so they keep getting smaller and smaller. And then we're asked what's the total area of all the squares. Okay, so how are we going to think about this? Well, we want areas, so we're going to need to know the side lengths of all the squares. And it's going to be easiest to start with the largest square because we don't have a smaller square, they just keep going. So it looks like we're going to start with this one and then somehow find out something about the others from this one. Also, it's worth noting this one rests on the axes, whereas to even know where this square lies, we need to know how wide this square is. So we'll start with this first square, and we'll just call the side length x, because that's something we need to find. And what else can we do once we know this is x? Well, often in geometry questions you want to fill in other lengths that derive from this. And one thing to notice is this distance here is going to be 1 minus x. We could also fill in this, which is going to be a minus x, but it's not so useful because there's more going on in this section. So we could imagine looking at this triangle, which we just found something out about. We know 2 of its sides. And then the thing to notice here is, okay, we've got a kind of repeating pattern. And what you often want to look for is some way of relating smaller features of that pattern to larger features. So you can get some kind of relationship, because you know you're going to have to find out about these small things from the big things. And it's not just the squares that keep getting smaller and smaller, there's also all these triangles. And the thing to notice here is that each of these triangles is actually similar to this large triangle. And that's because the top edges of the squares are all parallel to this horizontal, and the verticals are all vertical. So they're all right-angled, and then this angle, this acute angle at the bottom right-hand corner of this triangle and of the large triangle, those are all the same because they're all the angle between this straight line, slanted straight line, and the horizontal. So that means this angle is the same in all of them, this angle is the same, this angle has to be the same, and so they're all similar triangles. There's also something you can just, even if you can't express your reasoning, it's something you can just intuit from the question, although it's best to be able to explain yourself. Intuit from the picture. So in any case, you can recognise that these are similar triangles, and why is that useful? Well, because we now know the side lengths of this triangle, and we know the side lengths of this triangle in terms of A, so that means we can at least get x in terms of A. So what's the easiest way of doing that? Well, similarity means the ratios between the side lengths are the same. So one way of writing that is saying this side over this side, 1 minus x over x, is the same as this side over this side of the large triangle, which is just 1 over A. And then we want to rearrange that. So how can we rearrange? Well, one way is to do it like this. So we can just divide through by x on this side to get 1 over x minus 1 is equal to 1 over A. Then if we add 1 to both sides, this side is just 1 over x, and here we're adding a over a, so we get 1 plus a over a. And then to get x, we just turn both sides upside down. So x is going to be a over 1 plus a. And quick sanity check, we want this to be less than 1 because x is smaller than a, and it is because the bottom's larger than the top. Okay, so this is our value for x, but we need to find out the side lengths of each of the squares, not just the largest one. And then the thing to notice here is that we can do the same thing again. Imagine we just look at the next one and call the side lengths y. And now imagine cutting off the shape at this edge. So imagine we were just looking at this triangle, where now this height is x instead of 1 where it was before. But otherwise this triangle with all the little squares in it would just look like a shrunk down version of this triangle. And to be precise, this triangle and all the little squares in it is similar to this shape with all the little squares in it. because all the angles are the same. And that means the ratio between y and x is going to be the same as the original ratio we had between x and 1. So what does that mean? It's the same thing as saying where x was equal to a over 1 plus a times 1, to get to y we're going to have to multiply by this factor again. So y is going to be a over 1 plus a times x. And then we can see that for all the other squares it's going to be the same each time, because they're all similar, we're just multiplying by the same scale factor of a over 1 plus a. So that means that the nth square, if the first square has side length this, and we're multiplying by this each time, the nth square is just n lots of this. So the second one is going to be a over 1 plus a squared, third one is going to be a over 1 plus a cubed, etc. So it's going to be a over 1 plus a to the n. And we have to remember that we need the area, not the side length, but that's fine because we just square to get the area. So the nth square has area a over 1 plus a to the 2n, or a over 1 plus a squared to the n. And now we just need to add these up for n between 1 and infinity. Okay, so we said the side lengths are all this, and then the area is going to be that squared. So for the first one, it's going to be a squared over 1 plus a all squared. For the second one, it's going to be a to the 4 over 1 plus a to the 4, and we're going to get a to the 6, a to the 8, etc., all the way down. And what we have to recognise is this is a geometric series, because to go from one term to the next, we're just multiplying by a squared over 1 plus a all squared. So, in particular, we've got our first term is a squared over 1 plus a all squared, and when we do our formula for the sum to infinity, that goes on the top. And then on the bottom we have 1 minus the common ratio, which we said is also a squared over 1 plus a all squared. So this is going to be our sum. And what's the best way to simplify this? Well, notice we've got 1 plus a all squared on the top and the bottom, so we'll just multiply top and bottom by that. And that means we get a squared on the top, and on the bottom 1 plus a all squared times 1 is just 1 plus a all squared minus a squared. And then we can simplify the bottom. So if we multiply the bracket, we get 1 plus 2a plus a squared, and then the a squareds cancel. So we just get 1 plus 2a on the bottom. And that's our final answer. Just quickly, we might want to sanity check this answer as well. Is it the right sort of size? Well, one thing we know is this ought to be positive, which it is, because a is positive. And it ought to be less than the area of the triangle. And if we go back and look at the triangle, the height is 1 and the length along the bottom is a, so the area is just going to be half times 1 times a. So the area of the triangle is basically half a, and we want this to be less than that, so we'll just check that it is. And what's the easiest way to do that? Well, we kind of want to get just an a on top here. So if we divide top and bottom of this by a, we get a on the top, so we can compare to this more easily. And then 1 plus a from here plus 2 from here. And we want that to be less than a over 2. And that's fine because the bottom of this is 2 plus 1 over a, and a is positive, just from the diagram. So that means this inequality is true, so this is a reasonable answer.